So good morning. Let's start the lecture number 11 of the course on computer control. And this lecture is about parameter estimation in the presence of colored noise. Let's start by recalling one example that we saw. And in this example, I showed that whenever we have colored noise, and look here at the model, the noise is colored because it has a component related to the previous innovation E of t. So the previous white noise Z is a white noise sequence, but then I consider a noise which is made of the current sample of E and also the previous sample of E. So there is a memory from the previous sample. And what happens is that if I estimate A and B in the presence of this type of noise, then the estimate does not approach the true value. The true value is this straight line, and with colored noise, you are going to a value which is clearly above the by 20% of the true value. So, how can we tackle this problem? One possibility might be that we could estimate this parameter C. But we have a problem because we don't know E, okay? So if we had access to the noise E, we could have enlarged the vector of parameters to estimate by being not only A and B, but A, B, and C. Of course, our regressor phi would be Y of t, U of t, and E of t. And okay, that's wonderful. We estimated B and C, and this bias, this polarization in the estimate would disappear. The problem is that we don't know E. Okay? So one possibility is to estimate E and then use an approximation of E in the regressor. Okay? That's the so-called extended least squares. So one possible way of tackling this problem of estimating in the presence of colored noise is by using this extended least squares algorithm that I will present in more detail in a moment. Other possibilities are instrumental variables that we are not going to speak about, and the maximum likelihood method, which is the workhorse of estimation, and that you probably have heard in the basic course on statistics. Probably you've forgotten that. Some of you follow the course on digital signal processing, and they speak a lot about maximum likelihood. So my interest here is in discussing these methods, in particular maximum likelihood, in relation to system identification. So let's start by briefly saying something about extended least squares. So suppose that we have our regression model, linear regression model. Y of t is phi transposed of t theta naught. Theta naught is the true vector of parameters plus some noise. And the noise is correlated. So the noise is a weighted sum of past values of a wide sequence, of an uncorrelated sequence. Now, suppose that at time t, we have some estimate that I call epsilon of E. So the sequence E of t minus 1, E of t minus 2, E of t minus n is approximated by some signal that I know called epsilon of t minus 1, etc., epsilon of t minus n. So one possibility to do this estimate is to define it as the prediction error of y. Okay? So we enlarge our regression model by including the samples, past samples of epsilon, and the vector to include the values of c. So the estimation vector is enlarged by adding estimates of c1 and cn. And so we expect this to be small, but it's not 0, and we call it epsilon. So in a recursive way, we generate epsilon. Of course, we start with some estimate of epsilon that can be zeros, for instance. Okay, suppose that we assume that epsilon of t minus initially make t equal to 1, so epsilon of 0, epsilon of minus 1, and so on up to epsilon of t of minus n, they are all 0. Okay? And start with some estimates for c that can also be 0. So you are going to make an estimate of y, which is just phi transposed theta hat, and that gives you epsilon of 0, sorry, if t is equal to 0. So in this way, you go on recursively and you start filling this vector of epsilons for t equal to 1, t equal to 2, and so on. And you update the vector of estimates, not considering that it is just theta, but it's theta enlarged with the c's. So what we have, the algorithm works in this way. So I define an extended regressor, which is the original regressor plus the estimates of the white noise, and an extended vector of parameters to estimate, which is the original vector of parameters to estimate plus the coefficients of the noise, C1 up to Cn. And then we use the ordinary equations of these squares, but now with this extended regressor and yielding the extended vector of parameters. And then in the end, we, with the updated vector of parameters, we go on and generate this epsilon recursively. You have to think that time is progressing, okay? This is the extended least squares algorithm that is very much used, for instance, in econometry. Okay? So if you pick up a book on mathematical models for economy and finance, you will certainly see chapters on, or at least one chapter, usually more than one, on the extended least squares algorithm. And variations. There can be several variations to this algorithm. Now, extended least squares work. We have one problem because in extended least squares, it's like a bootstrap. A bootstrap is it's a type of algorithm in which you use the result of the algorithm in itself. In this case, we are using the algorithm to estimate the epsilons. And this type of algorithms, they have problems of you need to start with some reasonable estimate of the parameters. So a much more powerful thing is maximum likelihood that can be applied in to many areas, as you certainly know from other courses. So suppose that you have a random variable y that you want to estimate. Sorry, that you observe. And there is an unknown parameter theta that you want to estimate, and is somehow related to y. Okay, express this relation in the form of a probability density function. Okay, so the probability density function of y somehow depends on theta. And if you know this probability density function, you observe y and you want to infer theta from this. Okay. So remember this: if you do, if you have a vector of observations for y, then this function becomes a deterministic function because y is no longer the random variable; is the random the observations made of the random variable. So it's the value of the random variable for a particular realization. And this becomes a function of theta. Okay? And the maximum likelihood estimator works like this. So you define a function, which is the likelihood function, which is nothing more than the probability density function of y and theta. Okay, and you do an observation for y. This becomes a function of theta, and you find the value of theta that maximizes this probability density function. So we call this function the likelihood. That is why this is the maximum likelihood estimator. In many cases, P will involve an exponential, so you can work with the logarithm of the density of the likelihood function. Because the logarithm is a growing function, and if it is a growing function, maximizing P is the same as maximizing the logarithm of P. Now, suppose that this function logarithm of L is smooth. So if you want to maximize it, just with respect to theta, compute the gradient with respect to theta and equate it to 0. So the maximum likelihood estimator, I call it theta hat of MEL from maximum likelihood, is the value of theta that verifies this equation here. So the partial derivative of theta, if theta is a vector, this is the gradient with respect of theta of the logarithm of the likelihood function is equal to 0. Okay? To compute this maximum, the maximum of the logarithm of the likelihood function, in some cases, very few cases, you can actually do the computations by hand. In general, you have to rely on numerical methods to find this maximum. Let's see one example. Suppose that you are observing the value of theta, but corrupted with some white noise. Okay? Imagine that you want to measure the width of a table, and just a moment. So imagine that you want to estimate the width of the table. So the true width is theta, and you do measures, and the value of the measurements is y. So t equal to 1, that's measurement number 1. T equal to 2 is measurement number 2, and so on. So you do a number of measurements, and each measurement is equal to the true value plus some error. Okay, that's the sense of the noise in this case. And I'm assuming that the error is uncorrelated from measurement to measurement. So it's independent more than correlated. It's independent from measurement to measurement. Now, we have, suppose that we know the probability density function of E, and we assume it is of this type. Actually, this is a Gaussian zero mean unit variance Gaussian probability density function, but that's immaterial. So we know the probability of E, and we do a number of observations. So we have this capital Y is a vector of observations, Y1, Y2, Yt. And we want to estimate the value of theta using maximum likelihood from this vector. Okay. Now, since Y is theta plus E, the joint probability density function of Y and theta is nothing more than a Gaussian of the same variance and with an average which is theta. Okay, and this is for just one observation. Now, if you consider a number of observations, since they are independent, the joint probability of all the observations that I write in this way is the product of the probability density function for each observation. So if you have two random variables, the joint probability, if these random variables are independent from each other, the joint probability density function of the two variables is the product of the probability density function of each of the functions. Now, here, instead of having just two, we have t, okay? So t is one number thing. We have done 5 observations, t equal to 5. So I multiply the density functions of each of the observation. And I know that each of them is nothing more than it has this expression. So, but now with y replaced by the concrete observation IT. So by plugging this into this second formula, I get the formula in this last line. Okay, so I'm multiplying many terms of this type with y replaced by y of I. Okay, and remember that now this y of I are given numbers, so you have they are your observations. So this is a function of theta, because the vector y, which is made of this yi, is given. You have observed the data. So this is a function of theta. Actually, it's an exponential of a sum of squares. And I want to find theta that maximizes this function. So what shall I do? I will work with the logarithm. And if I work with the logarithm, then I have here a product of two terms, this term 1 divided by 2 pi up to t divided by 2, and this exponential. So the logarithm of this product is the sum of the logarithms. Okay, this term does not depend on theta, so it's not much important. And this term is the logarithm of the exponential. And by definition, the logarithm is the inverse of the exponential. So I just put the exponent here when I compute the logarithm. And now I compute the partial derivative of theta, which is of this term, of the logarithm of the likelihood function. And when I compute this partial derivative, this first term disappears. And then this is minus 1/2 the sum of squares. So the derivative of the sum is the sum of the derivatives, and each term is 2 times yi minus theta. Okay. So if you cancel the factor 2 that appears multiplying, it's a constant of 2 common to all the factors, and you divide by 2, and you get just this term. And now remember, you have the summation of all the data minus the summation of t terms equal to theta hat maximum likelihood. So when you sum t terms equal, it's t times theta hat. So if you solve this equation with respect to theta hat maximum likelihood, you get this expression, which is the sample mean of the sample mean of your observations. Okay. Now, one thing that you can see in this example is that with Gaussian observations, Gaussian noise observations, you end up here with a quadratic cost. So this is the same as what you would obtain if you would apply least squares to estimate theta. Okay? Actually, when you have uncorrelated noise and you have Gaussian noise, Gaussian and then correlated noise, so you have to ask for both things, maximum likelihood is nothing more than least squares. The advantage of maximum likelihood comes when you have correlated noise or non-Gaussian noise. Now, maximum likelihood has a number of properties. I will mention two. One is consistency. That is to say, when you increase the number n of observations, you are squeezing the probability density function whose maximum is your estimate. So you are the mean, the average mathematical expectation, better to say, of this density function is a true value of the parameter. So it's centered. It's a center estimate. And when you increase the number of observations, you are squeezing your density around theta rho. So it does not happen that when you go on increasing the number of observations, you get a worse result. So with more observations, you will always improve your result. Can be very little, but you do not degrade your result by increasing the number of observations. And it is centered. So these two properties. The other thing is that the maximum likelihood estimation satisfies the so-called Cramer-Hall bound. That is to say, the error covariance matrix is you cannot reduce it more than a certain quantity, which is given by this J. Actually, it's the Fisher information matrix, which is related to the information matrix that you have. So this means that there is a limit of precision of your estimator that you cannot improve beyond a certain point. In several cases, this is not exactly zero. Okay, now, the previous example is a very simple example. And we could do all the computations. So why is it simple? Because it's Gaussian, and more than Gaussian, the observations are independent from each other. So you can write the joint probability density function of the observations by just multiplying the individual probability density functions for each observation. In general, this is not true. And to build the maximum likelihood function and then to maximize it, it's can be a complete numerical task, and there are algorithms for that. In MATLAB, the system identification toolbox provide you with a function called Rmax. Okay, Rmax, remember, is the name of one model. Okay, it's a difference equation, the name of a difference equation model, but it's also the name of a function in MATLAB that yields an approximation of maximum likelihood estimators. So suppose that you have one system described by a model which is something like this. Sorry, let's go back a little bit. It's something like this, okay? So you have the theta to estimate is nothing more than the minus a's and b's, and then you have the c. So you are adding this extra term, okay? And you call, you call NA the number of poles, or the number of coefficients of A coefficients, and B the number of B coefficients, and then C the number of C coefficients, and NK the delay. So in this case, I was assuming that my NA was 4, and D was 1, and C was 4. This, and the delay was 1, okay? So this is data that you have to fill in, and you have, yes.
Sorry, can I make a question?
Yes.
In the lab, the professor gave an example which NA equals NC. The number of coefficients for the poles were the number of coefficients for the...
Right.
Yes, my question is, is there a strong reason for considering that, or is just a good practice?
There is a reason, in particular, in relation to your working lab. I will mention that in a moment. Okay. So after a couple of minutes, I will say something extra on that. Probably it will answer your question now. But the answer is yes. So playing with NC, in this case, I was using NC. Well, this is just an example of how to use the software, okay? I will now give you 2 examples, and we will discuss this. That this was just one example, how to fill the numbers, okay? In the how to use the software. But later we are going to see that in some cases, even if you don't have noise, it's useful to have to consider an NC which is not just 1, so correlated noise in situations where the order of your model is smaller than the true model of the plan. Okay, but we will discuss that in a moment. Okay. Okay, so this slide just wants, the objective of this slide is just to show how simple it can be to use this software. So it's just the first lines up to here, okay? All the other lines are exploring the model. So you do an experiment or a simulation, and you collect the samples, the numerical samples of U in a vector U, and the samples of the observed output in a vector Y. You have to decide which of these numbers you have. I will say something more in practical cases. So the difficult part is actually selecting these numbers. And then you collect all these numbers in this vector, and you say that TH is the result of the identification. Actually, in MATLAB, it's what we call a structure. So it's a kind of putting together a number of several numbers. And these numbers are the estimates of the different polynomials A, B, and C. So the coefficients of AI, BI, and CI. And you just say Rmax Z is the data, and N is the structure, okay? Then you can do a simulation and so on. If you want to do the estimate with least squares, use another function, which is Rx. You see here, Rx. If you replace Rmax by Rx, then instead of having an approximation of maximum likelihood, then you write here Rx. That's the name of another function. Of course, in that case, you don't need to specify NC. Okay? So now let's discuss two examples. One of the example is very simple. The other example is tightly related to your work. In this case, I have colored noise. It's a second order system. I didn't write here the equations, but okay, it's a second order system, and it has colored noise. And I use least squares. I use least squares to estimate the A and B polynomial, so the AI and BI parameters. And you see that our estimate, well, this is not so bad, but the estimate has some overshoot. So if you do a simulation with the same input, okay, to replicate the data, then you see that there is an overshoot that was not in the original data. Okay, so in the data that in the true data obtained from the true plant, well, the true plant here is the simulation, but I take it as true plant, does not have any overshoot, but you see that your estimates give you a model with some overshoot. Now, if instead of using the least squares, you use the maximum likelihood, this overshoot disappears, okay? So the overshoot was due to an error in the parameter estimation. Let's see a more interesting example related to your work. It's not exactly your work, because in this example, I'm assuming that I control the motor with an inner loop. So there is a measurement of the motor shaft. Shaft means veio do motor. Okay? Motor shaft is veio do motor. So I measure the motor shaft angle. So I measure the angle here, and I do a feedback. And I have here a PID controller, okay? Or a PI. It was, I think, a PI controller. So if you apply a constant tension here, the motor is not going to turn indefinitely, because a constant means a constant position for, because since we have feedback, I'm comparing the angle with this signal U. So my command to the motor is the position of the motor. Instead, in your work, I'm assuming that I don't have this feedback. So my command to the motor is the tension applied to the motor. And what happens is that if I apply a constant value of U, the motor will start spinning, spinning, spinning endlessly, okay? In other words, in the situation of your work, of your lab work, there is not this feedback. So this is more or less what? It's the dynamics of the motor, okay? Uncontrolled motor, which is one pole, one real pole, and together with another real pole at the origin, okay? And the pole of at the origin models the integral effect between the tension and the angle, because the motor starts to rotate. Here, since I have this inner feedback, the motor together with this controller becomes itself a system, and this is probably two real poles or one real pole, okay? And then we have the dynamics of the flexible bar, of the flexible R, okay, such as you have. And if you don't mind, I will change my slides to the Portuguese version, because I don't know why, but my English version, in my English version, these slides disappeared. Okay. Now, let's think a little bit about the dynamics of the flexible bar, okay? So your shaft is here, it's this signal, okay? This is the dynamics of the controlled motor. And I have, if I do a change in the position of the motor shaft, what happens? The bar is an oscillatory system. So the simplest model for an oscillatory system is a second order system, okay? A second order system with complex conjugate poles. Now, let's apply a step to the command of the motor. So this is not a step, but it's not much different from a step. And then you have this oscillation here. So let's see some actual experimental data. Okay, so, okay, these are some experimental data. So we had the bar more or less in equilibrium, and I applied one positive step to the motor, and I got this result. Now, my question to you, and this is not just a rhetoric question, I would like to say something, is what do you see in this picture? So related to the structure of, assuming that the model is linear, what type of poles and zeros you see here? Of course, if you have an artistic mind, you can say, this is a Picasso type sinusoid, okay? No, but okay, Marcelo, tell me.
Okay, we have a non-minimum phase 0 because we have the valley in the beginning before.
Okay, so I apply the positive stimulus and it goes down before going up, okay? Physically, we can understand this. You understand why?
Yeah, I guess so. It's like it's contrariating the, I don't know how to speak in English. É como se estivesse a contrariar o efeito do input.
This is because the bar works like a spring, and when you rotate it, I will now put the rotation axis in this direction. When you rotate it, it does like this, okay? It does like this, but it's like the initial part turns the other way around, okay? So you have an impulse, I call it a fishing rod effect. So we have a non-minimum phase system. And what type of pole is this, or zero?
It's a non-minimum phase 0, which means it's on the outside of the unitary circle.
Okay, so we could expect 0 outside unitary circle. Okay, and what else can we see here?
A pair of conjugate complex poles, because we have an oscillatory behavior, but it is decreasing as time passes.
So these poles are where? Inside or outside unit circle?
Inside the unitary circle.
Inside, not over the unitary circle. It's oscillating, so it could be.
Yeah, but it's decreasing the amplitude of the oscillation.
And so?
And so it's inside.
It's inside, okay. So I have, they are close to the unitary circle, but they are clearly inside because we have an oscillation. And then we have this Bottatoid effect. Bottatoid is a word that I just invented. Okay, what do you think? Is this noise? These deviations with respect to the, is this noise?
I would say so, but it might also be another pair of conjugate poles at higher frequencies, maybe with lower amplitudes.
Actually, it is. You can model your bar as a mass that is oscillating. That's the fundamental mode. But then you say, I split my bar in two parts. Okay, in two parts. One is faster, is lighter than the other, and this gives an oscillating dominant mode plus at a higher frequency another oscillating mode. Okay, which gives you these fluctuations. Okay, these are actually experimental results. Huh? What you receive in what you received for the laboratory that you are now doing, it's a simulation because you can't go to laboratory to do the experiments. But what you are seeing here is actually an experiment. Is actually an experimental result, and these deviations here, is higher frequency oscillating superimposed on the fundamental mode. So you have a fundamental mode that goes up and down and up and down, and it's decreasing in amplitude. And then you have a faster, something which is being of small amplitude and faster. Okay, and faster. Okay. Let's try. There is a principle due to a monk of the Middle Ages, I think this 12th century or 13th century, I'm not sure, called Occam, and he said, well, if we have two theories that explain the same thing, we should start by considering the simplest theory. That's, we call it Occam's razor, a navalha de Occam. Se nós tivermos duas teorias que explicam igualmente bem uma coisa, vamos escolher sempre a mais simples. So let's suppose that we have this is a real pole. Let's approximate the controlled motor by a real pole. And let's approximate the first mode of the bar. Okay? And so this gives me three poles. Okay, one from the motor. Actually, the motor has two, but I'm neglecting the fast one. So just one pole from here should be a real pole, and then two poles that I'm sure they will be a complex conjugate and stable. Okay, so three poles. And one or two zeros. I placed here 1 0. Okay, let's do an approximation. Then there is a moment you are going to see where it's you cannot justify your choices, depending on the fitting to the data. Now let's use least squares, okay? And the red is the data that I have, and the blue is the model that I got from least squares. What do you think about this model? No opinions? It's garbage, okay? It's awful. É uma porcaria de modelo, okay? In plain, well, I won't use the plain British English word, but it's very bad. I mean, even the static n is wrong, okay? So we can say, well, we have probably some high correlated noise. Now, let's improve the order. So instead of having three poles and two zeros, I have four coefficients in A and four coefficients in B. Okay, sorry, this is not two zeros, but 1 0 with two coefficients, because the B has two coefficients. This is wrong. So two coefficients give me 1 0. Now, now I have a model which is okay. It's oscillating. It replicates the non-minimum phase effect, but the damping is wrong, still wrong. Although you could design a controller that stabilizes the bar with this model, but it's still very bad. Let's see what happens if we use maximum likelihood. Okay, let's see. I will go back to those two slides. And let's go to the original 3 poles and 1 0, 2 coefficients, because we have D0 plus Z minus 1, B1, so that's one. And B equal to 2, that's 1 0. Okay. And then I have your NC equal to NA. So I'm estimating the correlated noise. And you see that now I model the non-minimum phase and the damping and the dominant oscillatory behavior. So by considering the fact that I have correlated noise, I could gain a lot. Of course, I could no longer use least squares, but I have to use maximum likelihood. Now, let's think a little bit about this correlated noise. Actually, what is the frequency response of the bar? The bar is, you can imagine that it is made of a number of metal particles placed together, and each of the particles oscillates in an independent way. So you have an infinite dimensional system. Okay, so you can have many modes of oscillating. For instance, one mode, if you want to make it vibrate, you have a fundamental mode. Then you have another way of oscillating, of making the bar oscillate, which has the double of the frequency, and then you could multiply by some integer number, okay, and so on and so on. So if you consider if you write the bar is described by a partial differential equation, okay, and if you look at the frequency response of the tip, then you have the first mode. It's a first resonant mode. So the horizontal axis is frequency and the amplitude is the gain. So you have a first oscillating mode. Then it decreases. Then you have another oscillating mode. Then you have another oscillating mode, and so on. In the data, we can see the first two oscillating modes. Then it's so fast that our recording equipment do not see them. Okay? Sometimes we can hear them. We hear something like bzzz. That's a high frequency oscillating mode. I can't tell you why. Probably someone with a very good ear for music will be able to distinguish, but I don't think it's possible. Okay, but we could see the first two ones, and we could, with that model, we could capture the first mode. Now, the other modes are modeling errors. Okay? And modeling errors appear as noise. And they are very correlated because the spectrum is not constant. Okay? White noise, the spectrum of white noise is a constant. And instead we have a number of frequency peaks. So some frequencies are more important than others. And this means correlation. And we can think in this way. Suppose that this is your true model, okay? It's true model. We know that A should have infinite order, but okay, let's think it's a finite polynomial. Now, we have a nominal polynomial AN. This N means nominal. That's what you say, well, I'm assuming that A is of order 2, for instance. And then all the rest that corresponds to the difference with respect to the true polynomial, I call it delta A. So this is modeling error. Okay? So I replace A and B by the nominal values plus the error in A and in B. Okay? And I can rewrite this equation as ANY equals to BNU plus the remaining part. I call it V, and the remaining part is this stuff here. Okay? What happens is that this stuff here has nothing to do with stochastic noise, but it's modeling errors, and it's highly correlated. So if you have non-zero initial conditions, which you will have because you are exciting the bar, this will appear as a signal, which is a disturbance that is highly correlating because it is oscillating. Okay, when you go up and down in a certain pattern, which is probably even periodic. Okay, so when something is periodic, you don't have any independence in time because you oscillate in a certain pattern. So even if you don't consider stochastic noise entering, the fact that you are using low reduced complexity model, that is to say, you are assuming that your model has an order which is smaller than the model that actually generated the plan, then you will gain something. In this case, you will gain a lot, as can be seen, by using a method that lives with colored noise. Okay? And that's why, that is why you could, with least squares, you have this rubbish for the order with 3 poles and 1 0, so 2 coefficients in V. But if you have a model with the same structure, but then you explicitly consider the correlated noise, then you could have a very nice estimate. Okay. Now, suppose that you want to estimate also this high frequency mode. Then the best I could do with this data was to use a model of order 8, you see. Then I can replicate more or less the data, but I had to use a model 8 in this case. Now, if I want to design a controller, what I want is to have a simpler model. So probably this would be the best model. If I start having high dimensional models, then I can get in. It's more easy to get into trouble. Well, the design is more difficult, but it's done in the computer. The problem is that you have much more degrees of freedom, and these degrees of freedom sometimes tend to go to places where you don't want them to go. So it's wise to have simple controllers, and if you can start from a simple model, okay, then you get a simple controller, and this is advantageous for the design, because you will gain nothing much with respect to the model which is replicates the high frequency gain. Now, going back here to my plot of the frequency response of the bar, this means that we have a controller that gives you a good response up to frequencies, up to this frequency band in this range. Okay, you could help the design process by filtering the data and avoiding these terms here. So one possibility might be you filter the data to get rid of these high frequency oscillations and then try to use least squares. But this is usually worse than using maximum likelihood. Any questions up at this point?
I don't think so.
Okay. The message is simple. The message is simple. So when you are in front of your lab project, try to use, of course, you know the model. The order of the model was, I think, 6. I can't remember it well, but I think it was 6. So maybe you can use a lower order model, but be careful that it's an advantageous probably to use to assume that you have correlated noise, even though the simulation does not include any noise. Okay. Now, before ending, I would like to make a couple of comments about selecting the structure of the model in a systematic way. Okay, this is not in the English version. It's not even part of the program for the exam, but let me spend 5 minutes just making this question. So suppose that you have your model with polynomials A, B, and C. C works for the noise. This is the so-called Armax model. So you have the autoregressive part, the exogenous part, the X part. Exogenous variable is the control variable that comes from the outside. And the moving average part, which is the moving average of the noise. That's why this is called the Armax model. Okay? And you have the problem that you look at data and you want to decide which values of A, of N, M, and then them that you should use. Okay? And one possibility is to look to use arguments such as I did. Usually you need a lot of simulations and testing with the data. But there are systematic ways of finding the values of M and N. And one of them is the so-called Akaike information criterion. Okay? So the Akaike information criterion is a measure of performance of your model that is made of 2 parts. The second part is the number of parameters. Okay, so if your model has a lot of parameters, the AIC, the Akaike information criterion, is worse than another example with a smaller number of parameters. The number of parameters is M plus N. Okay, and on the other side, you have the likelihood function, or the symmetric of the likelihood function. So you would like the likelihood to be high, that is to say the symmetric of the likelihood function, or of the log of the likelihood function, to be small. Okay, so this gives you the capacity of your model to be close to data. Okay, so here your model is close to data because you are putting a lot of degrees of freedom, and here it's because it's the intrinsic explanation effect of the model associated to the estimate of the parameters. Okay, and there is a trade-off between these two. So if you look at the function Rx or Rmax, sorry, it's not, they do not estimate the AIC, but they estimate something which is equivalent. Okay. Usually, so you could compute this thing. Well, the number of parameters is straightforward. The likelihood function is a little bit more complicated, but you do it using software. As I said, in Armax, they give you something which is equivalent to AIC, and you should try to minimize it. You should try to minimize it. Okay. And the archaic information criterion is usually very conservative. It gives you big number of parameters, bigger than needed. Another measure is the so-called minimum description length. Okay, this type of model figures of merit for the models, of this figure of merit for the model. They are based on information theory concepts, some of them complicated. And the minimum description length, you can compute it using these formulas. It depends on this epsilon is the capacity of this is your observations, and this is the estimate of your observations given your model. Okay, so you compute the average of your squared errors, and then you have this you compute the MDL using this formula. So you have one term, n is the number of observations, p is the number of parameters. So you have one part associated with the number of parameters, and one part associated with the capacity of your model to explain the data. Okay, and there is a kind of water bed effect between these two terms. In the case of control, neither MDL nor AIC are very much useful. That's why I've cut it from the program. It's important that I mention this to you, so I do it. But remember that we have always this trade-off: capacity of explaining the data, but using reduced order models. And that's it for today. Do you have any question?